Hey everyone, welcome to This Explainer. Today, we're diving into one of the absolute most beautiful and frankly complex engineering achievements in all of artificial intelligence. We're going to answer one seriously fascinating question. How exactly can a machine write music that has literally never existed before? We're going to pull back the curtain on the incredible technology making this possible.
All right, I want you to imagine something. Just complete silence. And then, out of that void, a single piano note appears. Then another, and another. Slowly, you start to hear an entire, emotionally resonant melody form. You genuinely feel something. But the composer, well, they don't have a beating heart.
It brings up a wild question. What if every single song you've ever heard could just be reduced to mathematics? Now, what's really interesting about this premise is how much it challenges our deeply human connection to art. It makes us ask if the spirit of a song, the actual soul of a symphony, can truly be captured by algorithms. Since the dawn of history, music has been this profoundly human experience. But technology? It's completely shifting that paradigm.
So, here's the absolutely crucial point to wrap your head around. Modern AI doesn't understand music the way you and I do. It doesn't have ears, it doesn't feel emotion, and it has zero cultural context. Instead, it's learning the statistical patterns hidden deep inside the sound itself. It's literally uncovering the mathematical language beneath every melody, every rhythm, and every harmony you've ever loved.
Let's get into it with Part 1, Music into Numbers and Digitizing Sound. To really grasp the massive scale of this problem, just think about this number, 10 million. A standard 4-minute audio track at CD quality, which is 44.1 kilohertz, contains about 10 million continuous, totally unstructured samples. To put that into perspective, right, a high-resolution megapixel image only has about 3 million pixels. Music is just vastly more high-dimensional and chaotic. If you ask an AI to model raw audio directly, you introduce these extremely long-range dependencies, and that makes it computationally exhausting to learn high-level musical concepts.
Okay, so how do we fix that? Well, engineers use this brilliantly designed pipeline to make this massive amount of data manageable. First, they take those raw audio waveforms. Next, they use some heavy mathematical techniques, like the fast Fourier transform or FFT, to carefully convert those waveforms into frequency-based spectrograms. And then finally, they use advanced neural audio codecs, like SoundStream, to shrink all of this data down into compressed audio tokens.
You can kind of think of these audio tokens as the AI's alphabet. By tokenizing the audio, we're basically reducing this massive chaotic waveform into a neat sequence of discrete, manageable codes. We're effectively handing the AI a vocabulary it can actually use to read and write. And these tokens are amazing. They embed crucial musical information from the basic melody and rhythm all the way down to the specific timbre of an instrument, all at a much lower compression rate. It makes it so much easier for the system to process.
Which brings us to Part 2, Teaching AI to Compose and the Learning Process.
Historically speaking, AI composition has evolved drastically over the years. Way back in 1957, early computer-generated music relied on simple Markov chains, which honestly were highly predictable. By the 2000s, things like recurrent neural networks and LSTMs were helping capture short-term melodies. But the real game-changer happened just recently with Transformers and Diffusion Models. These new architectures can process long sequences all at once, and they can even reverse-engineer clear audio signals out of pure noise. That's what gives us the breathtakingly high-quality audio we're hearing today.
To manage the sheer complexity of music, modern systems actually split the workload into a kind of hierarchy. On one side, we've got semantic tokens. These are the guys handling the creative structure, the overarching melody, the rhythm, the style, and even the lyrics. Then, on the flip side, we have acoustic tokens. These handle the super granular, fine-grained details, like the specific acoustic resonance of a wooden violin or the high-frequency breathiness of a singer's voice.
And this perfectly illustrates a really fundamental truth about generative models. The AI is absolutely not just copying past data. It's not just memorizing existing tracks and spitting them back out. When millions of songs flow into the model, it is genuinely learning the statistical probability of which note or harmony or rhythm should logically come next. It's literally composing through a highly sophisticated next token prediction task. It's building this intricate, massive web of mathematical relationships.
Moving along to Part 4, Prompt to Symphony, and generating the audio. So let's trace this transformation process. When a user inputs something, like a text prompt, lyrics, or a style description, it first enters an autoregressive language model acting as a generator.
This generator manipulates those high-level semantic tokens we were just talking about to form an intermediate representation. After that, a token diffusion model and an acoustic vocoder step in as the renderer. They carefully take those semantic instructions and render them into the final high-fidelity 44.1 kHz audio waveform.
Imagine you sit down and type a prompt exactly like this, an emotional orchestral soundtrack with cinematic strings and a hopeful ending. Now, models like Google's MusicLM don't actually understand English, but what they do is cross-reference semantic meanings learned from massive datasets like Mulan and MusicCaps. They map your descriptive text directly onto the acoustic patterns they've already learned. It's like watching words become mathematical embeddings, and then those embeddings bloom into sweeping strings, intricate harmony, and complete musical structure.
And that takes us to part 3, Beyond Human Music, and our interactive future.
Because the AI is generating music continuously through these tokens, we are honestly entering an era of real-time rendering. Just imagine video game storylines, AR and VR experiences, or adaptive movie soundtracks that generate unique, constantly evolving music, precisely tailored to your exact moment in the media. Your personal AI composer could generate a triumphant swell of brass precisely when you achieve a victory in a game. It's creating a completely interactive score for every single listener.
But here's the thing. The true power of this technology isn't about replacing human musicians. It's about lowering the barriers to music creation. By utilizing intuitive tools and symbolic lead sheets that AI can read and write, it empowers absolute novices and seasoned professionals alike. An artist can effortlessly audition totally new musical ideas, edit recorded vocals, and manipulate stems. It's really unlocking a whole new frontier of human-machine collaboration.
So, to wrap up our explainer today, I really want you to remember 3 definitive insights. Number 1, every song, no matter how emotionally complex it feels to us, is ultimately a pattern. Number 2, these continuous chaotic sounds can be perfectly represented by mathematical tokens. And number 3, AI creates music through predictive next token generation based on vast statistics. It's not doing this by memorization, and it's not copying the past.
It leaves us with a pretty provocative, honestly breathtaking thought about the future of art and engineering. For thousands of years, music has been the strict domain of the human soul. But looking ahead, the next great composer might not actually have hands. They might only have mathematics. Thank you so much for joining me on this journey through the numbers behind the notes. Keep learning and keep listening.